Hello everyone and welcome to a new episode of my Homebrew Spectrum Analyzer series. In this video and the next two ones I'm going to discuss the Log Detector board. The purpose of this Log Detector board is to take an input signal and to output the strength of that signal in the logarithmic domain. Remember that you're going to potentially put into the spectrum analyzer a signal that has lots of frequency components. And as the spectrum analyzer sweeps across the frequency range of interest, you're going to end up with a signal here that's always going to be at 10.7 megahertz, but it's going to be one of the frequency components that you're currently sweeping across. So that input signal is then converted to the logarithmic domain and sampled by the ADC. In this video, I'm going to discuss the circuitry, in particular the chip that is used to do this, as well as some rationale of why it is kind of important to convert this to the logarithmic domain. The next video will be testing and or debugging of the Log Detector board, and the third one is going to be some more of a hands-on test of the board to put it to use. So why are we interested in sampling in the logarithmic domain in the first place? Let's say you're building an instrument to measure signal power, like the spectrum analyzer. If you want to measure weak signals and changes in that weak signal, your instrument is going to be pretty sensitive to these changes. But this also means that if you apply a strong signal, you're probably going to overload your instrument because it was designed to handle weak signals and changes in weak signals. So it wasn't designed to handle strong signals. But on the other hand, if you are interested in these strong signals as well, and you design your instrument such that it is able to handle them, you're probably going to lose in sensitivity on the weak signals. So one way to cope with that is to use a logarithmic transfer function, which is what I have plotted on this graph here. The x-axis here is the input, and the y-axis is the output, and the graph here is just essentially y equals log of x. So let's say we're applying a weak signal. If we're applying a weak signal, we're going to be somewhere in that range because the signal is weak, it's low, so that's a small x. And that weak signal changes by a small amount, which means that we're moving to the right or to the left. That will result in considerable change in the output because we're exploiting the steepness of this graph in that lower range here. So we have high sensitivity for weak signals. At the same time, if we apply a strong signal, we have to move considerably more to the left or to the right to measure the same change. So that's a bit of a compromise. It's compressing the space of your input in such a way that you're sensitive to weak signals here due to the steep slope of the curve, while at the same time you're still able to measure changes of strong signals just in a less sensitive way. And this also makes sense in a biological perspective. For example, it turns out that if you're in a dark room, then you're very sensitive to small changes of light. But if you move outside and it's very bright, then you're not able to detect that same change of light just because the signal itself is much stronger. And that's exactly the same concept that is exploited here to get that compromise between weak signal sensitivity as well as not overloading the instrument when strong signals are applied. On a related note, showing your data in the logarithmic domain allows you to just see more. This is an example from Hayward's Experimental Methods in RF Design, but essentially it could be any book because these plots are always shown in the logarithmic domain. In fact, this plot on the y-axis, the unit is dB, but let's just not care too much about that. That's just a way of expressing one value relative to another one on a logarithmic scale. This is a little tuned amplifier here. This amplifier amplifies frequency components around the center frequency of 14 megahertz much stronger than frequency far off of the 14 megahertz. That's why you get like this peak here that just shows that frequencies far away from 14 megahertz are attenuated much stronger than the center frequency. Now, if we were to show this plot in a linear domain, we wouldn't be able to see much because we, as I discussed before, there is a lot of sensitivity with respect to weak signals. So in the linear domain, that would be pretty flat here. Because we'd have to compress that down in order to be able to go up to 0 dB here. So we would end up with a curve that is pretty flat and then rises rapidly towards the center frequency and then falls as rapidly as it was rising and then be flat again. So that wouldn't be too much of an interesting plot here. And that's just another way of looking at the problem and another justification for expressing stuff in the logarithmic domain. This is the schematic of the log detector board. As usual, there is a local power supply section here that's 10 volts in, 5 volts out, and this section is exactly the same as it was on the other board, so there isn't anything special here. Then there is the usual noise filtering 10 ohms plus a capacitor RC filter that I already discussed in previous videos, but the core of this board really is this AD8306 Limiting Logarithmic Amplifier. And we're going to discuss extensively how this chip works. Then note that there is an input port here where you put in the signal that you want to measure, as well as two outputs. One output is the limiter and the other one is the output where you actually get your logarithmic voltage. Now I'm going to focus on the impedance matching transformer here, as well as the chip itself. I'm not going to focus too much on the limiter because it's not used in the spectrum analyzer, and currently I also don't have any use for that. I will build it up just to show the output, but I don't think I'm going to use this in any experiments for now. Apart from that, there isn't too much. There is just a 2.7K resistor and a pretty small capacitor here, and that's just an RC filter. But other than that, all there is really this impedance matching network as well as the chip itself. So let's look at how you convert this input signal into the logarithmic domain. So how do you design a circuit that has a logarithmic transfer function? This is sort of an interesting question because, at least for me, that's not a part I design in every day, so I think it's worth having a closer look. You've got your input signal here that is fed into a chain of amplifiers. For the sake of this example, I chose it to be 4 amplifiers, and each of these amplifiers has a gain of 2. Now, these amplifiers have one key aspect, which is that they're limiting the output voltage at some limit. For example, let's say the limit is 2 volts. So if you feed in 0.1 volt, you get 0.2 volts out. You feed in 0.5 volts, you get 1 volt out. You feed in 1 volt, you get 2 volts out. But that's also the limit. So anything higher than that will get limited. Let's say you feed in 1.5 volts, you still get 2 volts out. And this is the key property that makes this whole circuit work. Each amplifier output is fed into a detector, which is, you can think of this as essentially a full-wave bridge rectifier. And the output is then summed up in this summing amplifier as well as low-pass filtered. So let's make an example to see how this works. Let's say the limit is, as it was before, 2 volts and we're feeding in 1 volt. The first amplifier, with a gain of 2, amplifies this to 2 volts, and any other amplifier is already limiting. So we've got 2 volts here, 2 volts here, 2 volts here, and 2 volts here. So in the end, essentially, we've got 2 volts everywhere, and we sum this up to 8 volts. Now, if I reduce the input signal by a factor of 2, so I'm feeding in 0.5 volts now, the first amplifier is going to amplify this to 1 volt, the second amplifier is going to amplify to 2 volts, and the remaining two amplifiers are limiting, so that's 2 and 2 volts. Now if I sum this up, in the end it would be 7 volts, right? That's 1 plus 2 plus 2 plus 2. But I'm going to make a little mistake here and neglect any amplifier output that is not limited. This is a mistake, but I'll come back to that. So in theory we have 7 here, but because I'm neglecting anything that is not yet limited, I just sum up these 3 here, and that's a sum of 6. Now if I reduce the input yet another time by a factor of 2, I feed in 0.25 volts. The first amplifier amplifies this to 0.5 volts, the second one amplifies it to 1 volt, the third one to 2 volts, and that's the limit, so the fourth one is limiting, is not amplifying anything, and that's 2 volts again. And if I sum up everything that is not limited, that's 2 plus 2, that is 4. So, and the same holds true if I do it another time, then I end up with 2. So in the end what I did is, I reduced the input signal every time by a factor of 2, and the output is reduced by 2. So I managed to somehow convert this multiplication and division to a subtraction, which is exactly what the logarithm does. So this seems to work, although, as I said before, I'm neglecting these non-limited terms here. So that's a bit of an error, and in fact, if you look at the datasheet, they tell you about this. They tell you that, of course, this is not perfectly linear. And in fact, what I did is I simulated the behavior of such a model here and plotted it. And that's what you see on this plot here. So essentially, this wavy line here is exactly what you get. Sometimes it's larger, sometimes it's lower, because due to the fact that this is not computing a perfect logarithm, it's just not linear. I also have to say that on this plot, the x-axis is actually on a logarithmic scale, which means that if you look at this logarithm here in a linear coordinate system, and you convert this axis to the logarithmic scale, then the whole thing would sort of get squished here, and you'll end up with a straight line if it were a perfect logarithm. But it's not. This is why you've got these lines, and in fact the dashed line here is the perfect logarithm. So so that's why you've got a bit of error here. You have to be aware of that error, and in fact, if you look at the datasheet, you get a plot that looks almost exactly like this, and that's just due to the fact that there is a bit of error here in these terms that are not yet limited. This is the first page of the datasheet of the chip that I'm using. And you immediately recognize that this is exactly this topology here. You've got a chain of amplifiers, you tap off with a detector each output of the amplifier, and you sum it up with a summing amplifier here. Now, this chip is a little bit more funky. For example, to extend the dynamic range, not only are they amplifying the input signal, but they're also attenuating it, and put 4 more detectors here in this attenuator path. That sort of, it's more of the same thing, but just instead of amplifying, you're attenuating, and you can extend your dynamic range by that. In addition to that, there is this limiter output here. And you can see quite nicely that the limiter output of the chip is just whatever you get out of this chain of amplifiers. So this is not low pass filters, it's not rectified, it's just sort of a limited amplification of your input signal. And then there is a few biases and an intercept term, but essentially this is it. So in the next video we're going to actually look at the performance of this chip. We're going to measure the limiter, the logarithmic output, and make sense of how you use the intercept to tell the signal strength that you put into this chip at the input. revisiting the schematic, most of this should make sense now. Actually, there isn't too much to it really. There is a power supply section. This is the logarithmic output that is filtered and fed into this output SMA connector. And everything that's left on the right side here relates to the limiter output. And it's not much either. There is two pull-up resistors because these are open collector outputs. And there is a DC blocking cap here, as well as another resistor to set the drive level of the limiter output. Now, on the left side, there is an input SMA connector that is routed to this transformer here, which then goes to the log limiting chip. And discussing this transformer is a little bit tricky because essentially this relates to impedance matching. The source here has a 50 ohms source impedance, and the chip itself has roughly 1K of input impedance, which means that the impedances are not matched. And actually, in RF design, impedance matching is probably one of the most important topics at all. And I didn't want to sneak this into the back door because I think it deserves some proper discussion. But I don't want to do it right now because honestly, this is not the best example to explain the topics. And so I decided just to link in an explanation to it for now and just assume that the impedances have to be matched. Because if the impedances are not matched, there is horrible stuff going on in general, and really you want to have 50 ohms of input impedance in that part here. So I still want to explain what this transformer does here, and that's why I have this little sketch here. And in the end, if you look at it, there is a generator here that's generating some signal and 50 ohms of source impedance. On the right side of things, there is 800 ohms of input impedance here, and these 800 ohms are actually the 1K of the chip in parallel with this roughly 4K resistor here. You can do the math and you'll see that this is reasonably close to 800 ohms. Now, if we were not to impedance match, we would connect directly 50 ohms of source impedance to 800 ohms of input impedance here, and then clearly there is a serious mismatch between impedances. So this transformer here helps matching these impedances. In general, you could also, there is many ways to do this. The easiest probably is using an L matching network. And in fact, you could do this because if you look at the block diagram, this input is always at 10.7 megahertz. So you could design an L match for that, but Scotty decided not to do that. And actually, I adopted that because I think that's pretty cool. The idea is that if you put an L match there, that match is only going to work out at 10.7 megahertz, and otherwise you'd end up with a mismatch again. So putting that transformer here allows you to get a pretty broad frequency range at which impedances are matched. And I will actually run an experiment where I demonstrate how this can be useful. So how does this work? There is a transformer here, and I'm going to denote the ratio between the secondary number of turns on that side and the primary number of turns here as n. So that's just n2 divided by n1. If you have 10 turns on that side and 2 turns on that side, n equals 5. Then from physics, you probably know that the voltage at the secondary side is the turns ratio multiplied by the voltage at the primary side. So that is U2 equals N multiplied by U1. And similarly, the current at the secondary side is the current at the primary side divided by N. It has to be like that, otherwise power wouldn't be conserved in the first place. And because impedance is just defined as voltage divided by current, you can plug in U2 here, that is N multiplied by the voltage on the primary side, and you end up with N multiplied by U1 divided by I2. And you can do the same for I2, because I2 is just the current on the primary side divided by N, as I just explained. So you end up with N multiplied by U1 divided by I1 divided by N. And then if you restructure this, this actually turns out to be N squared multiplied by U1 divided by I1. And U1 divided by I1 is nothing but the impedance on the primary side. We already used this on the secondary side, where we said Z2, the impedance on the secondary side, is U2 divided by I2. So that is N squared multiplied by Z1. And then if we solve for N, we end up with the square root of the impedance on the secondary side divided by the impedance on the primary side. Okay, so if we have an impedance of 800 ohms on the secondary side and 50 ohms on the primary side, that's 800 divided by 50, that's 80 divided by 5, which is 16. And the square root of 16 is 4. So in order to get a decent impedance match here, we need a transformer with a turns ratio of 4. And of course, that's exactly what Scotty designed in here and what I also use. So we have a nice match, and this input here looks like 50 ohms impedance, and is then transformed to 800 ohms and eventually 1K using the transformer and this resistor. Okay, that's it. So as I said, in the next video I'm going to build it up and test it or debug it. And then we'll run practical hands-on experiments using the Log Detector and some other boards that are part of this project, just to demonstrate that you can do interesting stuff if you have things in a modular way. I hope that was interesting. If you have any comments, anything you want to know in addition, or anything to share, please do so below in the comments, and thank you for watching.